one and all. I extend my warm welcome to all of you. Our distinguished guest, Dr. Bimlesh, our principal sir, Dr. Ravi Narayanka, IQAC coordinator, Dr. Kusha Tiwari, and to all our participants. It's indeed a proud moment for me that I got this opportunity to welcome you all for a valuable talk in my college. As you all know, today's topic is on sustainable polymers, which I think is a very relevant topic for our chemistry students. And basically, it's the need of the hour also to have discussion on such topics, which will make our students to think more about sustainable environment. And also they can think and come forward with their innovative ideas also how to deal with their problems related to the pollution, and moreover the good replacements for the hazardous materials which we are using as a raw material with such benign chemicals and polymers. I suppose this session turns out to be very fruitful to all of you. And now, not taking much time, I would like to give a brief introduction of our eminent speaker, Dr. Bimlesh. Her teaching experience is almost of 14 years, and she had a research experience also of almost 18 years. She her bachelor degree is from University of Delhi, and she did her masters from IIT Delhi. Then she did DPhil from University of Oxford, UK, and her postdoc experiences include from University of Oxford, University of Nottingham, and IIT Delhi. Later on, after her return to India, she received the Young Scientist Award also for the research on cardinal, a cashew nut industry waste. And then she joined in 2012 Shivnadar University, and now working as an associate professor in Department of Chemistry there itself. She is a recipient of several research grants, and her interest mostly includes green and sustainable environment, chemistry, synthesis of monomers and polymers sourced from agricultural and industrial waste for high temperature adhesives and non-composites, polymers architectures for PVs and OLEDs, nanomaterials and their derivatives synthesis for device applications, drug delivery applications, and antibacterial applications. To her credit also, she had 49 publications, 3 patents, 1 book, and 3 book chapters. I welcome you, Dr. Bimlesh, once again. Now, but before we start with a much awaited talk, I would like to invite our professor, our principal sir, Professor Rabi Narayanka, for the welcome address. But before that, I must say that sir is always a guiding force for behind all these programs which we are doing in our college, either physically or virtually. He is always there to encourage us and to support us. And sir, we are very grateful for you for your mentorship always. Thank you so much for encouraging us. And now, sir, over to you for a few words of encouragement from your side.
Thank you, Dr. Ashu, for
Thank you,
your
sir.
kind words. At the outset, I would extend a very warm welcome and good evening to all the participants, and especially to our star speaker of the day, Professor Bimlesh. At the outset, I am very happy to note that uh, SLC, we have been, our science courses have been taken up for the last many years, and which has started giving good results. And as a result of that, we have also able to start this DBT Star College program, under which this project is running. And for this reason, I must congratulate both the departments of chemistry and physics, and especially Dr. Ashu Gupta for mentoring this DBT Star College program. And we have able to clinch this. And any program would be successful with the participation of its teachers and its other stakeholders, like the main stakeholders are the students. So having said that, I am very glad to say this. With Dr. Ashu, Dr. Monica is there, and there is a team of keen researchers who have been working behind the scene, and a very bundle of energetic students who have been very active in participating in all these programs. And with this also in our college, the IQAC is led by Dr. Kusha. They have been bringing in pioneering conferences, seminars, and a lot of other very, very innovative kind of talks and lot of many other things, including I am very happy to state that the Unnat Bharat Abhiyan project, where we have been mentoring 5 villages also. All these things we have been trying to do is for the betterment of the society, and which is again directed towards sustainable well-being. So I am very happy that this talk is going to be delivered by such an eminent person, and I'm just going through the biodata. It's such a huge achievement, and I hope that this talk is definitely going to, as you said very correctly, Dr. Asu, definitely would like to give a direction towards this sustainable development. And actually, the area where we are also operating, madam, as you know, there are a lot of local issues which also needs local solutions. We don't need big solutions, where very, very localized solutions also can be helpful for the society. And these are the needs of the hour. So I'm at the same time very, very hopeful, and I must put, repose my faith and trust in these young colleagues. I'm sure that they will take it forward and definitely bring some sustainable solutions for the local problems faced by all this local population, including our adopted villages. The times are not far off when I would really like to see some concrete projects are being run for the success of these local problems also. So with these words, once again, Madam, welcome you very
Thank you,
much
sir.
for our seminar. And with this, also we would like to, when the pandemic is over, we would like to have you in person in also our college, where this one-to-one interaction will be taken to a next level, and you could really see the kind of, and your valuable suggestions will also give them and guide them to further channelize their energies towards, not only sustainable polymers, also towards sustainable development. Thank you. Namaskar.
Thank you. Thank you, sir. Thank you, sir, for such an encouraging words. Now I would like to invite our dynamic IQAC coordinator, Dr. Kusha Tiwari, to say a few words. Over to you, Dr. Kusha, please.
Thank you, Ashu, and I must welcome the speaker of the day. Madam, your profile is very impressive, as I was just hearing, and I'm sure that you will be an encouraging presence today for our students, and they will get to learn a lot of new things on the topic. I must congratulate the coordinator of the DBT Star College scheme for our college. That she's organized this event, and as our principal sir has rightly pointed out, that the main beneficiary of this particular project and all the events and activities that we hold are our students. And specifically, DBT Star College scheme is to inculcate the research abilities and highlight the research potential of the students. I'm sure that the series of events that Dr. Ashu Gupta and her team are organizing and will be organizing would definitely increase or better the research output of the college. The IQAC is always there to facilitate and help out and participate in such academically enriched programs. So I welcome all the stakeholders, all the participants, the resource person to this event, and I must thank Principal Sir for bringing DBT Star College scheme to our college. He was the one who actually worked very hard with this entire team to make sure that we become part of this scheme. So thank you so much to our principal sir and to the entire team. Thank you.
Thank you, Dr. Kusha. Now I'll invite our eminent speaker, Dr. Bimlesh, for her talk. Over to you, Dr. Bimlesh.
Thanks, Dr. Ashu, for inviting me. I'm really feeling very nostalgic whenever the college calls me, so I can recall all my old days. So it's a beautiful journey which DU has brought in me, and I'm really happy to come back to the colleges again and in future also. Thanks to the organizing team for giving me the opportunity to discuss our research activities in Shivnadar University to the new minds, which are basically, they are the one who think out of the box, and people like me are just channelizing their thoughts, and that's how research usually happens. So that's all from my side in terms of a brief introduction which you have provided is short a beginning in this era. So I'm really happy to come to the college also when this pandemic situation goes in a different moon, not here. Yes. So that's how I would love to be a part in the system. I also really thank this DBT Star College scheme. I think this has provided lot many opportunities to the college level, which was not at all during our time. So I think Dr. Ashu can recall those days also.
That's all.
So yeah. So without taking much time along this direction, I think let's go directly to this talk, which is on sustainable polymers. And as rightly said, it's an appropriate topic. And I remember when I was in Oxford, the work which I was doing is completely full of polymers and nanomaterials. And when I come back to India, I realize our country is far behind and we have to look for some local solutions which are appropriate from our country viewpoint. So that's how my journey started in this direction. And it's a completely different project which I was doing in UK and then in here. So sustainable polymers, I will be talking about this next generation phenolic resins. And I will also provide a brief overview like what we are working towards this energy solution, especially this lithium sulfur batteries. And in that direction, I will also talk about the flame resistant parameters. So my slides are visible?
Yeah, it's completely visible.
Okay, thanks.
Okay.
So I just mentioned over here who are we. So if you see it over here, this is we are nearly away from Noida. It's more towards Dadri. If it's not a very high traffic, like during morning hours or during late hours, like the drive journey is 1.5 hours. So you guys are also most welcome to reach out us in SNU. It's a university which was developed in 2012 and it's a fully residential, but the main orientation is research. It is available both at undergraduate or BSc students are doing many projects, which I will be bringing it here. And that's how we do it. And it's a very greener area. And the design is such it has preserved all the sustainable solutions which are around us in terms of greenery, in terms of lake, in terms of research, in terms of living. That's how we are doing it here. So I will be talking about polymers mainly, and just to give you a brief overview, we have a materials research lab which is there at SNU. And I'm really fascinated by this green chemistry, 12 principles which were given. And I'm utilizing those principles which are, they are more on the higher up the ladder, like 1, 2, 3, like that. And I utilize this for either towards the energy solutions or towards sustainable materials, especially the polymers. And since, latest drug delivery applications are also emerging out of this. So I'm the training which I have inculcate while abroad, I've utilized that for even for drug delivery applications. So in this direction, I move forward. So I think right now, especially I was talking to someone in Australia today morning, and she was mentioning in Australia also Delhi is known. And the reason which she said, I didn't feel good about it, but this is the fact. It's the pollution. Okay. So if you look at this, the climate change, which we are bringing up in the society due to a lot of human activities. Yes. So these are the main problems which we are creating. And I think we all have to think in that direction. Can we provide some better solutions to better living? Because if there is any pollution or something, naturally it's coming back to us in other ways. So it's a circular pathway. So health and diseases are getting deteriorated. So in this direction, I put my research topic here. So why renewable resources? Okay. So if you recall back, like during earlier 1850s and all, it's a coal revolution which was there. But before that, there is renewable feedstock, which people don't talk about it much more. So these feedstocks which were there, like people use it, but they found like coal has come up as a brighter energy solution. They start using not only for getting the feedstock out of it for synthesizing many chemicals, polymers, you name anything, it's mainly sourced from coal. However, it's if you see, the coal has come up with such a bright future, even though it's dark black in color, it has got lots of issues associated with it, and that's give rise to think, can we look some other opportunities. Thereafter, natural gas come up in the picture. You must be aware, like especially in Delhi and other places, like instead of using a petroleum origin like resources, now CNG and other gases are there for driving the vehicles. But now the future is again changing. So if you see the surge also along this direction, like now the next will be electric vehicles. Okay. So that's what is happening. And if you look at this petroleum driven research, it's very attractive, easy for time being. But at the end of the day, it's belonging to non-renewable category, because if you see all the petroleum reserves, it takes several ages to convert into coal and other products. Yes. Another issue is the non-biodegradability. Everyone is using lots of polymers, but they are not thinking about whether it's really required to use it. And this question mark lies should be lying towards everyone's head. Yes. So we are generating lots of waste, and the energy demand also is increasing day by day. So in this direction, we have to think like, can we have this sort of closing the loop? And naturally, there should be some way. And greener solutions are the mere picture towards this direction. Sorry about it. I think there's a slide issue. Yes. Let me go quickly. Just 1 second. There's some, yeah, that's better. So greener solutions, which are belonging to the renewable category, or if it is not belonging to renewable category, can we use some waste materials which is there, which we are generating day by day? Can we utilize it for providing some sort of solutions to our present generation and also for the future generations too? So in this direction, since the topic is about sustainable polymers, and if you look this phenol formaldehyde polymers, I hope Dr. Ashu students are learning polymers also in undergraduate level. So if you look at this phenol formaldehyde polymers, it is long back, like Leo Baekeland has invented it while they are working with some phenolic and formalin. He just mixed it up and he found like the polymer mass, it's become like a gluey sort of thing. And that's how the invention happens. And if you look at this bakelite, phenol formaldehyde polymers, is in our everyday need. Okay, right from lower end applications towards higher end applications. Okay, so in the aeroplane also there are lots of composites which are there, which is containing this phenol formaldehyde with glass woven or carbon woven fabric. Lot many applications are there. So if you look at this polymer, even though it's invented such a long back, 1907, it's 2020 right now, and till now no one has looked for a solution towards it. Can we replace with something else? And if yes, what is the solution, and can we able to overcome its drawback? Because the next challenge is, can we move one step ahead of it? So if you look, this is a typical chemistry reaction. Reaction of a phenol with formalin. You can use acid or base, and it leads to electrophilic aromatic substitution reactions. Naturally, ortho and para positions are more reactive, and it can form a three-dimensional cross-link network. Okay, so this polymer is brittle in nature. If you look, there are not many small-scale industries which are just providing this phenol formaldehyde resin And it has the problem of poor shelf life. If you store it for 6 months at room temperature, it goes bad. What these people do, it's very cheap, so they throw it away. No one is bothered like how they are throwing it. So disposal has also always an issue. Yes, if the low cost is associated, you will not think either once like while throwing it. So these sort of things are giving lots of problem. And another issue is it has got limited thermal stability. So people, students, these young mind, like they must have seen, like it's written BPA Free Plastics. Yes, and this BPA is nothing but this is the bisphenol A. Okay, and it's formed by the reaction of phenol with acetone, and it's a typical reaction. And it looks very nice, phenolic component, but it's the importance is of it is has a rigid and a bifunctional nature. Bifunctional is the phenol source, and bifunctional, beside bifunctional, it has a rigid. So if you look, it's linked towards this isopropylidene linkage. So this looks very attractive, and so far no other phenolic component is able to replace this BPA. So now the polymer people worldwide, they are looking for this replacement, and the reason being it's act as a xenoestrogen, which means it mimics estrogen like properties, which leads lot of problem which people are not forcing it, especially in India they are not looking at that direction, but surely it will give a huge amount of problem in future generations. So where is this sustainability? Can we think of some alternative material? Yes. And if the alternative material is there, then what are those? Okay, if they also behave in a similar fashion, then it will become a problem. Yes. So if you look, especially in India, people who are in southern part of India, and especially in towards Assam origin and all, cashew is like vastly available. Yes. And like Diwali has just gone, cashew, if you see, like we are one of the major consumer of this cashew nut in India, and also like Arabian countries and all. So if you look at this, there's a mesocarp. There's a mesocarp on top of this cashew apple, and this is usually thrown out in the field after its usage. Yes. So we are not encroaching towards the cashew nut which we are eating. It's the waste which is coming out is thrown out in the field for either for incineration or just thrown away. Okay, for degradation. Even animals are not those who understand this cultivation, they can talk about, like even animals don't feed on this cashew nut. If when it's raw, it cannot be munched because it has lots of phenolic content in it. And this is the beauty. India is like larger producer of this cashew nuts, and the waste generated, now people are looking, there are so many small scale industries who are looking for its production, and they are sending this material, exporting it in large tonnage also. Okay, so this mesocarp which is there is rich in these phenolic components. If you see it over here, so there are a lot of phenolic components which are available in there. So this is the major component which is known as cardinol. Okay. So if you look at this, these are the other components, and this is the major one, which is the anacardic acid. It's a orthohydroxybenzoic acid. And this is a typical reaction which you have learned in your undergraduate level. Like orthohydroxybenzoic acid has got tendency of, when you are heating it, it can undergo decarboxylation reaction. So as a result of this, while you're heating this oil which is oozing out of this mesocarp, while you crush it and all, so it can lead to the formation of more cardinol, enrichment of cardinol at the expense of anacardic acid. So this can be used as a major phenolic component in polymer industries, and lot many surfactants, polymers are upcoming in this area. Okay. It can be a good substitute for petro-based phenols, and the extra functionality can also be utilized for further modification. That's why the polymer chemists are being known, and even the synthetic chemists. Another component, lignin. If you look, lignin is rich in lots of phenolic component. Okay, and commercially, glycol can be easily sourced from it by pyrolysis of this biomass. India known for this agricultural resources. So this is another phenolic component which can be sourced from greener origin. Another is this isoeugenol and eugenol component. Isoeugenol has got double bond over here. This is the eugenol. So eugenol is present in the clove oil, and you all know what is a clove oil. I don't have to say much. So this is another phenolic source. So if we know all these phenolic source and we are aware like problems associated with phenol formaldehyde resin, and Henkel is one of the MNC, like which is industry abroad, and Kanika, Huntsman, and they have got a composition which is based on cardinol, and they have made a polymer resin. When I went for this ACS conference back in, I think, 2012 or 13, and then I found like they have got a patent also in this direction. And like it's sourced from India, like what our country is thinking along this direction. So that's how I started. I really got a kick over there, and I started thinking along this direction. And if you look at a new generation of polymer was emerging around that domain, these are known as benzoxazines. And if you see, the cost is similar to phenolic and epoxy polymers, and they have got better properties. Okay, if you look at the flame resistant characteristics of polybenzoxazine, it does not catch fire at all. Yes. So looking at this direction and this look at other polymers, they are like highly tunable to this flammability behavior. So if this is the case, then polybenzoxazine be made from out of cardinol, and that's how I started working towards it. And if you look at the major component, this is a new class of thermoset resins, and this is made from phenol and amine. You need a formalin. Nowadays, people are also looking for replacement for formalin also. Yes. So it's a simple condensation reaction. You get this benzoxazine monomer, and water is just coming out of this reaction. So it's highly atomic in terms of making this, and the byproduct is just water. Okay. And it can undergo ring opening polymerization. The ring cleaves over here, and it can lead to this polymer. Okay, and it has got very beautiful properties. And the last one, if you see surface free energy, it has got the capability to even replace Teflon. Okay, which is there in our cookwares. Yeah. So this is a cyclic heterocycle, as from chemistry point of view, it's a cyclic heterocycle, and it can be synthesized this monomer by solution or solventless method. But as from chemist, if I just vary phenol or if I just vary amine, I can design lot many benzoxazine monomers of different kind and depending upon my need. So what is the problem? If we look for this solventless synthesis, because the polymer industry require large amount of monomer, it cannot work with small quantity. So if I'm looking for monomer synthesis in large quantity, and if I'm doing solution-based chemistry, then it's basically like rate of reaction is slow, because you know the concentration of reagent is low in solution if you add more solvent. So this is one issue, and there is volatile organic compounds are also releasing out in air. So it's again coming back to the same square, health and environmental hazard. So can we look for some alternative? Yes. If I do solventless synthesis of benzoxazine monomers, especially the bisphenol A one, and after a particular time the stirrer starts, okay, you will not be able to do complete reactions. Okay, you cannot realize really good conversion of monomer. There is always trapped unreacted phenol and unreacted amine. Okay, and if these are trapped, there are lots of chances it can undergo ring opening polymerization. I think this is beyond the purview of today's work, but this is one of the problems. And I'm aware like these are the natural occurring phenolic sources, and which have got the potential to replace the petro-sourced phenol. So in this direction, cardinol is the first choice because it's a byproduct of cashew nut industry, and India is one of the major producer for it. And there are other phenolic component. India is agro-rich industry country, so we can look for other alternatives also. So I started working on this cardinol. If you see it over here, this is the cashew apple, and this is where like on top of it, there's a coating onto it, which is giving you this cardinol, and it reacts, it forms this monooxazine. Yes. And if it's a monooxazine, naturally it's a bifunctional type. So it can only form linear polymers. Okay, there's some sort of steric hindrance over here, so it will not lead to high molecular weight polymers. But if I take I change it, instead of monoamine, I take a bisamine, then it has got tendency to form this bisoxazine, and it can lead to a cross-link polymer. So because it became a tetrafunctional structure, so it's as a both solvent as a monomer. Why is it so? Because there is a long alkyline chain which is C15 long, so it can act as a reactant as well as a solvent. So that's give the solventless synthesis benefit to these reactions. And if you look, this amine reacts with bisphenol A. This is what people are trying. When they are doing it without solvent, then the reaction does not happen. Okay, because of this issue. And how it can be achieved by this methodology, you add this cardinol in one pot, it can do a conversion of making this cardinol benzoxazine and a bisphenol A based benzoxazine. So this was the clue which I got in the initial days, and I realized like this is probably the way forward. And I'm not going into the details of these data. Please do not worry, the youngsters. Just look at the columns which I'm just pointing it out. So this is the greener component. This is the petrosourced, yes. And if you look, the temperature at which this ring opens up, in case of a bisphenol A, it opens up around 180 degrees centigrade, and in this, it opens up around 240. So why industry will go when it has to invest more energy to do this ring opening polymerization? So this was one of the challenge which I found. And another important aspect which I found, this is not pro for the cardinol benzoxazine. Another important parameter which we can notice over here, the thermal stability. Once you form the polymer, it should not catch fire. It should be thermally stable. It should not degrade with heat very quickly. So if you look at this, the bisphenol A1 can degrade at a lower temperature as compared to this. So this is a benefit. It's a sort of crisscross matching. Okay. So looked at this behavior, what are the benefits and what are the gap area? Can we think of some alternative chemistry? And we looked at the structures, which is a parahydroxy benzoic acid, and this has got acidic functionality. And acidic functionality, you must have learned acid and base catalyzed reactions in your earlier reactions, and you know etherification and deetherification. If we looking for ester hydrolysis, then acid and base catalysts are very good. So considering the similar sort of scenario, I'm just bridging up that sort of knowledge. So this is something, it's a ether sort of linkage, but actually it's not called ether in polymer chemistry, but right now I'm just using this terminology. It has got tendency to protonate over here, and it assists this ring opening reaction by this acidic protons which are there. So this is only acting as a monomer, but also it provides a source of acidic hydrogen. So yes, if we do this sort of synthesis, what will be the benefit? So if I look, do not look at all this, just look at this last row. This is a phenol formaldehyde resin, which I talked about, the bakelite. It undergoes polymerization at 160 degrees centigrade. And if we go towards the industry and say, use our product, then they will only go if it has got similar polymerization temperature. And during those days, we were able to achieve like similar ring opening polymerization temperature as phenol formaldehyde resin. And all earlier resins like this one, it's a liquid, like a flowy material, very low viscosity. And polymer industry don't want, unless until any specific application, if they are looking for solvent-free processing, they will go for it. But if you look this phenol formaldehyde, it's a solid powder. Okay, so we got a solid powder which has got similar properties like this. Apart from that, it has got very better thermal stability. So that's how we started looking in this direction, and then we started knitting. You must be aware, like as I mentioned, if it is more cross-linking, yes, it will give more thermal stability. So if you look at in this structure from there, cardinol, we have made monoxazine, bisoxazine. If you see, this structure is like folding it over here, it's a trisoxazine and it's a tetraoxazine, and we are able to cross-link it better and better. And that's how we started looking at the research. But understanding like the basic reaction which is happening. If we understand the basic concept, then we can start flourishing the research around it. And if you look at this, the cross-linking is happening by simple electrophilic aromatic substitution reaction. So how it's happening? So this is one of the ring opening intermediate which is forming out of it. This is the iminium ion, and this is the ortho position to the hydroxyl group. So it can react over here, and it can react at para position, and it can react with another benzoxazine monomer from these places. Yes. So if this is the clue, if we increase more number of benzene rings naturally, then it has got more tendency. So this is the tritylaniline which we have used it, and we really found the cross-link density is increasing in this domain as indicated by activation energy required for polymerization. So there is a substantial decrease in activation energy of polymerization. If you see, the monooxazine based on aniline is 143, but with tritylaniline, which is also a monooxazine, it has got lower value than this. So this is the clue, and we started working in this direction, and we start tailoring the structure at the molecular level. And this is from eugenol and isoeugenol. So this is the eugenol one, and furfurylamine is another from cellulose source. We have used it, and we have made these some sort of structures. If you look, this is because of the ring conjugation, which you have learned in your basic chemistry courses. Like, they can undergo ring opening polymerization, and once it is forming this phenoxide ion, it has got resonance stabilized. But when we look at this eugenol one, this is not in conjugation. So naturally there will be an effect in the property, and that's what we looked at it in the optimistic direction. And we found the properties of isoeugenol versus the eugenol one are drastically variable, despite like just one small change in the structure. And we are able to play around with this monomer in lot many applications. So I will talk about one of the major application which we used for adhesive application. And adhesive is nothing but these are the metal plates. So on the metal plates, we put this the monomer, and we don't use any solvent. That's what we are doing, solvent free or solvent less processing. So we use directly the monomer and adhere these substrates, and it basically act as a glue there. It polymerize, and then we use this instrument which is there in IIT and in DRDO. This there, but now we have also got in SNU. So over there, it's a tensile mode. Like pulling, how much energy is required to pull it and to break it. That's what we are measuring. So we are measuring the adhesion strength. So in that way, we have looked at various monomers and polymers, and we also look at the literature values, what people have reported. And if we see this phenol formaldehyde resin has got lab shear strength adhesion is around this value, but our synthesized cardinal-based structures are far higher. And if you look, the cardinal one is able to go further higher and higher. So in this direction, we also looked, can it lead to a halogen-free flame retardant? If you know, all your pipes and this electrical coatings onto this wires, conducting wires. I think Havel's advertisement used to come where they have this coating, and they used to cook some food with that wire. So that advertisement can probably provide you a clue. But in most of the commercial polymers, people add halogens. And if you know, if we are burning any halogen containing polymer, yes, it can lead to lots of corrosive gases in the atmosphere. Okay. And if you look at Delhi and especially India overall, so if we generate due to by some accident, some mishappening is happening, then this can lead to lots of choking also. Okay. The person will not be able to save the life. Okay. So in that case, we looked at this cardinal benzoxazine, and we made the polymer. Look at the flammability test. And if you look at this, it has got, look at the flame size. I'm not looking at this text. Look at the flame size. It's very high. And there's a flame drip. Means while it's catching the flame, it starts dripping some sort of plastic out of it. Yes. And this is a very hot plastic. It can lead to other hazards to the human mankind. Yes. So it's like a lap. Yes. So this lead to lots of problem. If you see this polymer, nothing is left on the pan. But if we have used this phosphazine framework, so this is without halogen. So this actually, it's a nucleophilic substitution reaction which is happening over here. The Cl goes away. So do not look, I'm also using the halogen. It actually goes out while you make the monomer, the initial stages only. Okay. So we have added this into this polymer and the flame is reduced, and simultaneously, if you see, more we add this structure, it has got more flame resistant. It's not burning at all. And simultaneously, we also looked at how much smoke is getting generated out of it. So smoke intensity is also further reduced. So we have understood like cardinol can be a good polymer source for polymer structures. Also, incorporation of any halogen-free reagent can also provide the benefit. In another direction, we also looked at as you know, like we also got some expertise on nanomaterials. So we have understood like polybenzoxazines undergo ring opening polymerization temperature is very high. So can we reduce it? That's the next challenge. And while doing this reduction, can we provide some additional opportunities for application? So if you look in these structures, what we have used some iron oxide nanoparticles, and then we tried to polymerize along with this monomer. So we found, besides reducing the ring opening polymerization temperature to 140 degrees centigrade, because it leads to lot many other linkages which were not there initially in the polymer. So it forms a highly cross-linked mass, and it has got magnetic properties also. This is a magnetic retriever, just to show you like it's get adhered to it. This is another work which we looked into this direction. And that's what is happening. The ring opening polymerization temperature is as high as this, but as soon as we add this iron oxide nanoparticles, the ring opening polymerization temperature decreased substantially. Yes. So this was one of the achievement which was published there. So we are working towards several bio-based benzoxazines, and that's how our journey is started. And we are also looked at chitosan, which is sourced from chitin. And in this work, the ring opening polymerization decreased to just 70 degrees centigrade. Now we are hoping towards reducing it to room temperature. That's what my students are currently working on to it. And we also try to replace the amine to some biological amines. So if you look, we have, this is the petrosource bisphenol A. Adhesion strength of our current work, which is published last year, like we are able to achieve a higher adhesion strength. So I think I should move towards this flame-resistant lithium sulfur batteries, which is another forte. If you recall, like in our household, there are lead acid batteries. Yes, lead is not good. I hope you know the reason behind it. Then comes the nickel cadmium or nickel metal hydride batteries, especially in this webcams and all. You must have noticed it. And nowadays, generation is moving towards lithium ion. Yes. So these lead acid batteries are still there in our household, especially for inverters and all. There's no way like people are looking for alternative, especially in India. I don't know the reason, but if you look, the energy density, energy it can provide in that volume is very much crucial. Okay, either as mass per unit mass or per unit volume. This is what people are looking, and Tesla, you know, it's one of the first electric vehicle made by this company Tesla, and they have got this lithium ion based vehicle which is coming. So people are looking alternatives from petroleum or diesel based, looking for this battery direction. And if you look, this is the lithium ion battery which has got this much of energy density. Okay, the commercial one. Okay, can we, if we look at this energy density, that means we have to have charging stations very frequently at a very frequent distance. Yes, and especially in India, it will be a challenge. But if we can design some sort of battery which can store similar amount of energy or more amount of energy, that means it can run at a longer distance without the need of charging. Yes, so this are the alternatives which worldwide people are thinking it. And we also thought in SNU, and we think some alternative. And I was reading some article and I found across this lithium sulfur battery, and I started looking in this direction. So if you look this lithium ion battery, they how they work and all. So it is a chemical energy gradient in which there is a lithium metal anode, and lithium ion just moves over here. It gets interconnected into this metal oxide framework, or people have got this graphite also there because it has got interlayer spacing. A lot many architectures are coming up in this direction to store more energy. So lithium ion goes in there. Yes, during the charging discharging process, it comes back out like this. That's what we are getting the energy from. Yes, so it's basically while you're charging your mobile, that's what is happening, and while discharge happens, lithium goes back in its own place. So this process is happening several times, but there's a life associated. This is again giving a lot of issue. If battery is not performing well, and there are chances of lots of hazards also. So lithium sulfur battery is providing more energy, and in these there is a sulfur which is used as a cathode source. So besides looking at this mono positive species, there is a di-positive species which can store more energy. So in that direction, people are also doing research on. But we looked at lithium and sodium ion because lithium India is not having much lithium reserves. Somewhere in Kerala, they are talking about something. I'm not aware of it, but yes. So in these directions, can we have a choice beyond lithium ion battery? And the solution is yes, lithium sulfur battery. So in a better battery direction, if we look, we have to look for the cost perspective, because nowadays the car cost is not much, but it's the battery which is involved in there. It's costing a lot of money. And can we boost its capacity in terms of like more energy in less size? So naturally, if the battery size is reduced, it can move a longer distance with less energy consumption. And what about the safety issues? If you have heard about this news, like flight return back, yeah, to the original port because of this battery catching the fire and all. So there are a lot of alarms which usually you must have noticed while traveling. Yes. So there are safety issues. And how about this raw materials? Okay, cobalt oxide which is used, it's very costly. So naturally the cost is also boosting up. And what is the sustainability aspect? Once we use it, then we start throwing this battery also back. Yeah. So these are the various issues. And if you look, this lithium sulfur battery has got several fold higher energy density than the current lithium ion battery. And sulfur is one of the industrial waste. Okay. Petroleum industry is generating it. It's abundantly available. They don't know the usage for it. So it's very low cost, and it be utilized as providing a cheaper battery and with higher energy density. Another important component is cardinol, which India is the leading producer. And based on that, we started looking at this. If you see, this is the sulfur mountain, and this is a bridge. Okay. People don't know what to use this sulfur for. And you must be aware this terminology, vulcanization, which you have learned. So we are doing inverse vulcanization. I will talk about this very quickly, and we can do reaction up to kilogram scale in solventless medium, and it's just a 10-minute reaction. Okay, so that's how we are working towards it. I think this is an important aspect, so chemistry aspect. So sulfur undergoes this ring opening polymerization at 159 degrees centigrade. It forms a diradical species. And this is the temperature which is known as the sealing temperature, where there is an equilibrium between forward and backward reaction. Yes. So if somehow we can, the Le-Chatelier principle, so if we can move this in forward direction, naturally we have to start consuming this polysulfane radicals. Yes. And it's a diradical. So that's work very much good. So it's a bifunctional. This is also bifunctional. It can easily form polymers, and where the reaction will happen at the double bonds, at the oxazine ring, and it can form some sort of random copolymer. Okay. So we looked at that direction. We had made the battery out of it along with our collaborator. And we have used the RGO, which is again made through sustainable route. This is beyond the today's talk, but feel free to write back if you need some information. And then the battery which has come out has got very good potential. So this we have published. And we also looked for alternative to lithium, like, in especially lithium reserves are not there. And then we are again importing it. So again, a cost is associated with it. Can we look for some other alternatives? Sodium is there. So, but sodium cannot go for electric vehicles. There are other issues, but we started exploring our copolymers in this direction. And if we don't use this copolymer and we just use elemental sulfur, the battery does not work. Okay, so that's the take home message. So cardinol based monomers can act as good copolymeric material with this sulfur. Okay, so if we look at the flame retardant, as I said in my initial slides, like halogen free flame retardants, what people outside our country, they are looking for this flame retardants in the electrolyte. Yes, and if you look at the electrolyte, they are basically, if you look at this, it's based on the fluorine containing. Okay, some people also looked for the phosphorus containing electrolyte. So instead of that, we started looking for some copolymer, and it's a take home, the same take home message. So this is the phosphazine framework, and we have got this double bonds at the outside. I mean, and we know from rubber chemistry, yes, vulcanization, which is long bank came, yes. In that case, the sulfur cross-linking is happening at a where you use the sulfur content 1 to 58%. It's a very low quantity. So there is a large amount of sulfur if we want to get used into it. So naturally, we should have got more functionality. If you look in this structure, we have got like 6 double bonds and the outside periphery, and these are more susceptible for these reactions. So that's what we have done, and we confirmed like bio and petro sourced raw materials can be an effective way to react with sulfur, and the copolymer which is coming out has got flame retardant properties. So that's what we look. This is the sulfur, and the other one, I think I should start the video. So you see, this is the sulfur one, and this is the copolymer which we have made. So if you look, this is a blue flame over there. This is the sulfur. And if you look, it's a yellow flame. And we know like blue flame is very, very bad. It's had got very higher temperature zone. So if you look, this copolymer, after a particular time, they both are run, it just stop. It's a self-mitigation. Yes. And this is still continuing. Okay, so by this we have found like sulfur itself, if we want to make some battery out of pure sulfur, it's not going to give us a longer pathway. So we have to look for some alternative materials, and that's what we started looking for, these polymers in this direction, and we found they are far better than other reported structures. So this is one domain. And if you look at another greener sustainable approaches, this is again elemental sulfur. We also looking for this nanomaterial formation in another nanomaterial sheet, because we need the conducting matrix, which is graphene, which we are using it. So these are coming in nanomaterial, this one, yeah, nano size sulfur domains, which are forming in these matrix. So we are also looking in that direction. These are again greener approaches. If we can achieve the lightness with higher reactivity, nanoparticle versus the bulk polymer, naturally the reactivity will be different with lithium ion. So in this direction, we are also looking for this domain. Just to confirm you, like who are we and what we are doing, we have got many instruments in SNU, and students usually do all these experiments themselves. We don't have any people who can look for this specific instrument. We have got hardly 1 or 2 assistants who assist this, but its major drive-way
Yes,
force
sir.
is through our students. Yes.
Hello.
Yeah. Ashu?
Hello. Yeah,
Yes.
baby. Yeah, Dr. Bim, you continue. Sorry.
Okay. And these are our research laboratories. If you see, it's a highly sophisticated one. People do the
Yeah,
reaction
Dr.
with the
Bimlesh,
fume
please
hoods.
continue. Sorry, there was a call. That's why.
Okay. So it's we have got fume hoods where people do with the proper safety regimen in there. And these are our typical labs. So these are 2 of my students. I would like to say over here, like this is my acknowledgement slide. And I think students are the pillar. They only provide the ideas, and we work together in a more synergy. Like sometimes students provide the idea. That's why I said they also provide the idea, because if there is no synergy, because one man force cannot lead a longer pathway. I always a strong believer of it. Okay, so I give an opportunity to my students to think, and really, I don't know whether they are happy about this thinking or not. That I never asked, but yes, I made them to think. Like, I give certain projects which is driven by me, but I also say think out of the box. You should also have some component which you want to do in your research work. So I'm really happy, like, seeing this sort of freedom among my students. I would like to thank, like, Nagarjuna, whose work I have presented over here. Swapnil was one of the pioneer students who started working with me. She was my first PhD student. Monisha is another PhD student who is working towards the battery direction. Saad Zafar is working towards nanomaterial. And there's recently a latest addition of Sangeeta and Vaishali. Vaishali is from DU. I have got some PDF students also, which are now at different places. So undergraduate students, our undergraduate students like Shivani, Veda and all, they are also part of these research projects. Okay. So they have got the huge potential. The last year of their undergraduate study, they do full-fledged project for a 1 year. I would like to thank the funding agency, DST, CSR, DRDO, SNF, for providing me a lot of funds so that our students can utilize that and do some latest research. I thanks my collaborator, like Professor Sagar Mitra, who does the battery fabrication with me, and these three people, Professor Richa, Professor Seema, and Shalja, they are towards drug delivery. Dr. P.K. Roy is very close friend of mine, so we usually exchange many ideas. So that's all about SNU. And thank you for giving me the opportunity to talk. Maybe I have taken some few minutes more, but
No,
I
no.
will hear your questions now. Yeah.
Yeah, thank you so much. Thank you. It was really a good work you're doing. It's amazing. I could send my students there also so that they can all be trained with some your work which you are doing. It's really remarkable. And before I'll thank you further, but if we can take some questions, if we have in chat box, can we, Dr. Bimlesh, can we take some questions?
Yes, please.
Yeah.
Yeah.
So for that, I'll invite my student Aviral to take this forward. Aviral, can you take the questions if they are in the chat box?
Yes, ma'am.
Over to you, Aviral. Yeah, please.
There's one question.
Yeah.
Since sulfur is very big in size with respect to lithium and also has low conductivity as of lithium, it expands more during recharge and may lead to faster degradation. So, ma'am, is there any way to resolve these issues using graphene or any other method?
Yes. Very apparently very correct question. So whoever is asked, you are thinking out of the box. Most welcome to SNU. Join the research group. Yes. So sulfur is
He's by
non-conductive.
one of the best student, Aviral.
Okay. So like I guessed it right, Ashu. Yeah. Yeah. So if you think like sulfur is non-conductive, and that's why people are looking for conductive matrix. If you see in my slides, I have not talked about much, but we are using RGO, multi-wall carbon nanotubes there. Yes. So the main idea is when it reacts with sulfur, it does not form like Li something. It generally goes down to LiS8 to LiS2. It goes down in several steps during this cyclic voltammetry process. So during this, if it is happening, yes, so you need the conductivity because electron needs to move outside this electrode, and the lithium ion is doing the intercalation. So during this is known as like there is a volume change. When lithium comes and react with sulfur, naturally it leads to a larger size. Yes. So what happens is the cathode, which is there, it starts breaking after a particular time. I have not shown that slide over here. So as a result of this, the battery fails. Okay. So people are looking for alternatives. Those who have got very well-defined labs, what they are doing is they are just storing this sulfur in conducting matrix. So that's how they are doing it, but it's not an economically viable solution. So what we are doing is we are just mixing with a conductive material, which is RGO or multi-wall carbon nanotube. And if you see our recent work, which is happening, I've just shown one slide, we are looking for sulfur in nanomaterial size to increase the reactivity of it and it should go to the nano domain. So that's what we are doing. Very perfect question. I really liked. Yes.
Yes, ma'am. Ma'am, there's another one. How can we make plastic sustainable?
Okay. So sustainability means something which we can use and reuse. This is one way. This is one way. Another way is like when you use the polymer. Yes, this is known as recycling. There are various modes of recycling. Another is like the raw material which is used, yes, for making the polymer. They are of sustainable origin. Like in our work, what we are using is cardinol, eugenol, isoeugenol, guaiacol, various other these feedstocks, and these are vastly available. Yes, so by using them, like we are providing, we should not be looking towards petroleum reserves. So these are sustainable source. This is one thing. We have not looked so far. No one has looked at the biodegradability aspect of these polymers. That's another way. So sustainability can be in terms of reusage, or it can be of biosourced, or there is another third class, which is polylactides. What you see is they undergo unzipping reaction. Okay, what does it mean? The polymer, when you used it, it will be reacted with some acid or some enzymes, and it gives back you the monomer. So this is unzipping reaction. So this is also possible, which is the third type. So surely in our future work, or maybe the pioneer like you, they can look for the biodegradability aspect also with this synthetic bio reserve. Yes.
Thank you, ma'am. Ma'am,
Aviral, anything else?
Yes, ma'am. There's one more.
Okay, one more. Then because due to paucity of time, we'll wind up then. Okay,
Okay,
one more question, Aviral, please.
It's from Vansh Koshar. He's asking, what are the reasons we are a lot behind the foreign countries in using these methods, which you have explained?
This is if I say something, it will be politically incorrect. So I think we are not lagging behind. We have got a lot of brainwave, and if you see in India especially, lots of like people are not going for sciences, rather they are going for quick jobs, like especially engineering, yes, and other jobs. And once in the jobs in engineering, they are also only going for computer. I think this is what you can feel it. So it's basically leading to brain drain. Yes, what happens is India is producing this and they all go abroad. Yes, and they don't want to come back. So this is one thing. Another thing is like not many people are going towards basic sciences, but nowadays people are also looking in that direction. Especially in SNU, we have got a seat limit of undergraduate is only 30 students. We cannot take more than that. Yes, because we want to have a good teacher to faculty interaction, and our projects and our even undergraduate labs are very well tuned. Yes, so that's how it's happening. And I think people like you can, if they look for research further, then I think we will not be lagging behind. We will be running much more faster than ever. I hope I have answered.
Yeah, well said.
Thank you.
Yeah. I suppose we'll wind up. Aviral, is there any other further important question? I don't think so.
Anyway, I would like to say here to students.
You can mail to her, or you can mail to me. I can further mail to Dr. Bimlesh for your questions if you have now, because it's almost 5:10. I suppose we should wind up. Sorry for that. We'll wind up. Aviral, is it okay?
Yes, ma'am. It's fine.
Yeah, fine. Thank you so much. Thank you, Bim. Thank you so much. It was a truly remarkable talk, and it was very informative and well explained session. We are grateful for the time and effort you took and to share your thoughts and experiences with us. I believe that our participants, especially my students, will take along with them from your such an highly knowledgeable lecture. The way you touch all aspects of sustainable polymers was exceptionally good. Thank you so much once again, and we hope to join with you soon again.
Pleasure is all mine. Yes.
Yeah, I love to send my students to you for further training. Really, it's nice. I was amazed seeing your research. I have one question, but I'll ask you on a mail.
Yes, yes,
later
sure.
on. Yeah.
You can
And
phone me
further,
afterwards.
give me 5 minutes more, Bim, because I am being the coordinator. I have to propose a formal vote of thanks also for this successful webinar. For that, I am immensely thankful to you for once again for enlightening my participants, especially my students, and also my deep sense of gratitude I want to give to my principal sir for his keen interest, guidance, and always active involvement he took for all our activities we do in our college. And especially I owe my deepest thanks to our students team, and especially I would like to thank my 5 students, that is Aviral Singh, Vansh Kocher, Prachi, Niharika, Aditya, for their all efforts and the kind support they give to me. And without all this webinar would not have been successful. Thank you so much, all of you. I also express my warm appreciation to all my technical staff and the admin staff, especially Suman from my computer department. At the end, thanks to all our participants for being so engaging and supportive. Kindly, please, I request all of you switch on your camera so that we can do have a one screenshot. I require it. Kindly, please switch on. Dr. Bimlesh, can you stop your slide presentation so that we can have a screenshot?
Yes, yes, sure.
For all, yeah. Kindly, please switch on your camera so that we can have a screenshot. And Aditya, are you there? Aditya? Aditya Parashar. Aviral, is he there?
Ma'am, he is there.
To
I'll just-
kindly, Aditya, can you take the screenshot when all of our participants switch on their cameras? Please, all of you switch on your cameras. All of you who are comfortable, we can take the screenshot. Aditya, please do it. Please do the needful. Take 2-3 screenshots shots so that we can find out which is best. Then we can. Are we done, Aditya? Aditya, please respond. Aviral, is he there?
Ma'am, he is there. I'll just.
Has he taken the screenshot?
He is asking for stop the screen sharing. Yes, now it's available.
Yeah. Are we done, Aditya? Done.
Yes, ma'am.
Okay. Yeah, done. Thank you, Dr. Bimlesh, once again. Our college.
Bye.
Thank you so much. Thank you all. You can leave. Thank you. Please fill the feedback form. All of you, please fill the feedback form before leaving the webinar.
Yes, ma'am. I'll just inform them again.
Yeah. Mail them. Okay.
Okay, ma'am.
Oh.
Disconnect session, ma'am. Ashu, ma'am. Ashu, ma'am. मैम डिस्कनेक्ट कर दूं? ठीक है, अभी डिस्कनेक्ट कर दो।